In this video, we're continuing our discussion of methods to solve ordinary differential equations. So we were going through different solution methods for initial value problems, and in this video, we're specifically going to be talking about Heun's method. So Heun's method provides a slight modification to both the implicit and explicit Euler methods. So consider again the initial value problem. Dx dt is equal to a function of x and t. If we assume that the value of the dependent variable x, say xi, is known at an initial value ti, then we can write the expression shown here. So we're just integrating both sides of this equation. So if we do this integral on the left-hand side and then evaluate, so basically dx dt, or the integral of dx dt is going to be just x, and then we evaluate at the limits of integration, so ti plus 1 and ti. So x at ti plus 1 is equal to x at I plus 1. By how we've defined it. So this, we get the expression shown here on the right. So xi plus 1 minus xi is equal to this integral of f of x and t dt. So now we can use the trapezoidal rule, which was one of the methods for numerical integration that we introduced in the previous chapter. So if we write the trapezoidal rule for one interval from ti plus 1 to ti, or between ti plus 1 and ti, then we get the expression shown here. So xi plus 1 minus xi is equal to h times f evaluated at xi plus 1 and ti plus 1 plus f evaluated at xi and ti divided by 2, and this is order h cubed. So this is all from the trapezoidal rule, where this error term, this order h cubed, is inherited from the use of the trapezoidal integration rule on a single interval. And this is the implementation or the estimate of our xi plus 1 as using the Heun's method. So using this estimate, the local truncation error is proportional to the cube of the step size, and so the total error over the whole interval is equal to, is order h squared. So it's proportional to the square of the step size. So just bringing the xi to the other side of the equation, we can implement, or this is our estimate using Heun's method. So this provides an estimate that is better than both the implicit and explicit Euler methods. So here we had that it was order h squared, and if you recall, the implicit and explicit Euler methods were both order h. So we can note that this method is essentially a slight modification of the Euler method, in which the slope used to calculate the value of xi plus 1 at the next time point is just the average of the slope at xi and xi plus 1. So if this f evaluated here is the slope at xi plus 1 and ti plus 1, and this is the slope evaluated at xi and ti, then basically we're using just the average of those two to help us find our value at of xi plus 1. So Heun's method can be implemented in two ways. First is we can use the slope at xi to calculate an initial estimate for the slope, or for xi plus 1, which we can call xi plus 1 with the superscript 0. And then we can find the estimate for xi plus 1 based on the slopes at xi and xi plus 1, 0. So basically we calculate this kind of intermediate value and then use that along with xi to be able to calculate our xi plus 1. And the reason we need to do that is because we only know xi, so we need to find some estimate of our xi plus 1 so we can find this kind of intermediate value. The other option is to use the Newton-Raphson method or another root finding method at each time step to solve directly for xi plus 1, which we saw makes it an implicit method like the implicit Euler method. For here, we will only adopt this first method, where we calculate the an intermediate value. So this approach is called the predictor-corrector approach. So where the predictor is this intermediate value xi plus 1 superscript 0 is equal to xi plus h f evaluated at xi and ti. So we're using the explicit Euler method and the slope at xi and ti to calculate this intermediate value, which is our predictor equation, and then we correct our estimate using the corrector equation, so where we then use this along with our estimate, our slope at xi, to get our actual estimate xi plus 1. So let's repeat one of the examples we considered in the previous section using Heun's method. So consider the nonlinear initial value problem. Dx dt is equal to tx squared plus 2x with the initial condition x of 0 is equal to minus 5. And we want to find the values for t from 0 to 5 with h is 0.1. So Heun's method is implemented by first assuming an estimate for xi plus 1 superscript 0 based on the explicit Euler method. So we're evaluating our dx dt at what we already know, xi and ti. And then our next estimate is calculated as the average of the slope at this xi plus 1, 0 and xi. So let's see how this is implemented for the first few time steps. So x0 is equal to minus 5, t0 is equal to 0, t1 is 0.1, and h is 0.1. So our initial estimate, or this intermediate value, x10 is given as shown here. So x10 is minus 5 plus h times our function evaluated at x0, which was t0 and t0. So t0, x0 squared plus 2x0. Plugging in our values, we get that x1 superscript 0 is equal to minus 6. Now we can use this information to calculate the slope at x10 and use that to estimate our x1. So now x1 is equal to minus 5 plus h over 2 times the function evaluated at x0, t0, and the function evaluated at x1, 0, our initial estimate, as well as t1. So plugging in our values, we get that x1 is equal to minus 5.92. We can do the same thing for the next estimate. So now we find this intermediate value x2, 0 by evaluating our function at t1 and x1. So plugging in our values, we get that x2, 0 is minus 6.7535. And we can use this information along with our values at time step 1 to calculate our x2. And we can, when we plug in all the values, we get that x2 is equal to minus 6.556. And we can proceed iteratively to give the values up to t is equal to 5. So this was implemented in MATLAB, and the output is shown here. So using a step size of 0.1, we get a very good estimate of the function for this example. And we can compare this with the explicit Euler method result for this example. So you notice that where t is between 0 and about 0.8, the function varies highly in comparison to the rest of the domain. So we have this large kind of variation in the function here, where it's much smoother up here. So both the explicit Euler and the Heun's method provide a good estimate once we're in this kind of smooth area of the function. But during this area of rapid change, you can see that there's a big difference in the accuracy with the Heun's method versus the explicit Euler method, where Heun's method is able to provide a much better estimate of the exact curve.